All right, recording started. Okay, good morning. Today's topic will be Introduction to Power Quality. So before we can defining the power quality, let's imagine there is something simpler, something like that can happen frequently. Like you're at home and the lights don't go off fully off, or there is some blink or dim in the lights. It can happen for a second, or sometimes like your laptop charger get warm, or sometimes the Wi-Fi resets or the TV restarts without a power outage. It's just like some dim or some blinking in the lights. So you might consider this as a power outage, but it's not a fully power outage. So it's not a complete blackout, but you still had a problem, like something wrong happening in the electricity at home, making the light dim, making the some problems like the Wi-Fi resets, as an example, TV restarts, and so on. So what's this? Is this really a blackout? Is this really, I mean, circuit breaker turned off and turned on for or like something like that? It is the power quality. So power quality is basically the health of the electricity that we deliver. It's not just there is a voltage or not, or there is a current or not. Uh, the thing in the power quality is not about on or off, power on or power off, but it is about if the voltage is at the right level, like for example, like in Jordan, the residential 230 volts, 50 hertz, is it within that? Within this region, or within like plus minus tolerance in the voltage plus minus 10%, or I would say in the frequency plus minus zero point 0.5 hertz? Is it within the right level? Is the frequency stable? Is the waveform clean, like smooth sine wave? If it is not, this is called harmonics, which is something, or the sine wave is not pure sinusoidal, because as we know in AC, or the generation of AC, it is based on sinusoidal waveform. So is it pure sinusoidal or not? And are these like the spikes or dips that can confuse the equipment or make the equipment's damages, or I would say like impact on the equipment's overall equipment's performance? So here is the point. In modern power system, power quality matters more than ever because loads are not as the look like the loads old days. In the past, we the loads are basically motors, heaters, lamps, fluorescent lamps. But today we have power electronics loads everywhere, like rectifiers, chargers, electric vehicles chargers, your cell phone chargers, LEDs, computers, variable speed drivers, UPS systems. So all of these devices are efficient, they are great, but unfortunately they are sensitive and sometimes they can create a power quality issues. So I would say the power electronics is a source of bad power quality, and we can use it as well to solve power quality problems. So again, like the power electronics are considered as a problem of the power quality, and they can be used as well to solve power quality. So the thing here about it, which is when we used to have the old loads, like based on RLC, like for example, like the motors RL, equivalent circuit around RL, or sometimes we can have some other loads or load like the heaters, etc. So all of them in the past or the old loads, there is no problem in that the system can, I mean the problems are low with respect to the modern loads when we have like the renewable energy system connected through three-phase inverter to the power system, and when we have the rectifiers. All of this do have a bad impact into the waveform of the currents and the voltage as well. So this can make in which is inject harmonics. When there is a rectifier, there will be a harmonics injected to the system. And these harmonics can be significant more and more when we have multiple devices or when we have a lot of devices that are causing of this nonlinear loads. So I would say the power quality problems can be increased if when there is a nonlinear loads, as an example, power electronics application, of course, including the applications like chargers, LEDs, computers, variable speed drivers, etc. Okay, so the our roadmap, then we will start to a practical definitions. What does power quality mean in real life? Again, we answer this, which is how the power quality impacted us, like when we see the flicker on the lights, or sometimes the reset of the Wi-Fi or the reset of the TV because of that, when some a bad waveform happening. The other thing, which is why do utilities and engineers care? Because those can have a bad impact. Because basically it can create some problems. Like basically, you see the power is continuous, or you see you're still receiving the power, but is not pure sinusoidal, which creates a bad impact into your power, to your devices, and can make a poor performance as well. And then also we need to classify the problems. If we do classify them, how can we solve them? How can we solve the power quality? So he will talk about the power quality. Like again, it is a vague word. It's confusion, but we will talk more about like what's called surge, glitch. So the thing engineers need precise definition so we can coordinate measurements and make sure the system is in a good level or not by basically writing a standards. So we basically we can say if the system within the standards, we can guarantee there will be no power quality problems. Standards, what do I mean by standards? Like for example, like we need to make sure the voltage value between this range, the current frequency between this range, the THD, which is the total harmonic distortion, will be very low within a specific range. These, if we can guarantee, like there's a checklist, if everything within the same power quality problem, I mean within the same classifications, we can guarantee there will be very few or very low power quality problems by making the standards. So again, also by we will make sure like talk about the main source of the power quality problems from the supply side or from the load side, or it can be also from the interaction between them. It can be from the load side if you have a nonlinear loads. It can be from the interaction between the load and the source when we have a grid connected systems with for example, renewable energy. The renewable energy is also supplying a load, supplying, supplying a current or supplying a power. So the renewable energy is also, when we have a three-phase inverter, it can inject harmonics into the system as well. So we can say the load can be a source of the power quality problem. The source can be a source of power quality problems, and the interaction between them can be a source of power quality problems. Okay, so let's talk more, um, like talk about very practical definitions on the power quality, which is basically any electrical power system problem disturbance that results end user equipment not operating properly. So by the end user or the customer, if there is something wrong with it, this means something wrong. It's not like full trip the power. I mean, you still have the power, but it's not working properly. Then we would say this is a power quality problem. Then this is powerful because it shifts the focus from what happened into the network to what the customer experienced. That's the thing. What happened in the network, this is related to the power protection. We need to make sure there is continuous power operation, but the power quality is something separated, which is basically we are focusing on the what's the customer experience. Make sure the customer is getting the best waveform, or the performance, overall performance must be the best. Now, like notice something. That's not something important. The power quality says that equals the voltage quality and mentions frequency, amplitude, and distortion. Um, I would say it's not only about the voltage quality, it can be as well, you can include the currents. But the thing here, why they mention the voltage, because for most customer equipments, what they are see is the voltage waveform at their terminals. If the voltage magnitude sags, then if the waveform becomes distorted by harmonics, or if the frequency drifts, equipments may misbehave. So the overall thoughts, or I mean the vast majority, when we look at the power quality problems, related to voltage quality, but I would say it's not only about the voltage quality, you can say like the current, but again, when we are like as the utility companies, when they are looking at the customer side, they are looking at the voltage because that's what they are supplying the customers. So the voltage waveform at the terminals, and make sure the voltage waveforms at the terminals are fine. If there is a distortion, then of course this will make some misbehave in the equipments. And also here we see like there's a large economic loss, with different studies report that different numbers depending on what they include interruptions only versus power quality events plus interruptions. So we will say that, for example, LBNL work published through OSTI discusses national scale costing of outage and power quality impacts, and how earlier ERPI figures where they were used in such estimates this quantity. So which is like the power quality can cost the United States around 120 to 200 billion dollars. Now let's bring it back to Jordan. So in Jordan, if we don't have, I mean, the we don't have actually the quote US dollars amount, how much this money Jordan loses because of the power quality. But the thing here, the overall idea about the mechanism of loss is the same. So because the electrical system very similar. So we would say that since it's cost around 120 to 200 billion dollars in the United States, then definitely it will cost a significant amount in Jordan because like it's the same process, same steps, equipment risk, production scarps, it's like data loss and maintenance headaches. So all of them they can be applicable to Jordan as well. So definitions of power quality standards in IEEE framing. We can connect IEEE standards, as I said, like the power quality to maintain, like the system is working well regarding the power quality problems. So we like standards can be used. So here we can see like the reference IEEE 1000 or 1100, the Emerald Buck, and the IEEE 1159. IEEE 1100 focuses on powering and grounding sensitive equipments, electronic equipments, and IEEE describes it's a collection of consensus best practice to enhance equipment's performance while maintaining safety. So this is like the thing about it. But actually 1159, that was in 1995, which is heavily tied to monitor and consistent description of power quality phenomenon. Basically, how we define events and how we measure them, how we talk about them, like so engineers don't misunderstand each other. So let's say, or like IEEE is telling us power quality is not just a good voltage, it is also about a proper grounding, wire compatibility, and interaction among devices. So again, it's not only about the voltage, good waveform, but it's also about the grounding, wiring, interactions, etc. That's why in real buildings you can have perfect utility voltage, but bad bonding or bad grounding creates noise and equipment problems. We will talk more about grounding next. I think next lecture, because there is a separate introduction about the grounding and the grounding problems next lecture. But here, just like I would like to mention that the grounding can create problems. So for example, I've seen a computer lab where the utility supply was fine, but the grounding was poorly done. As a result, random PC reboots for no reason without disconnecting the power. It's just like because of the poor grounding, the random PC reboots. Network switches resetting, students blaming the electricity, while the real issue is not the electricity. The electrical utility company will tell you, oh, I mean, we've monitored the voltage. It's according to the standards, IEEE standards. There's no power quality problems. So, okay, what's the reason? Since it's not a power quality problems, you will see like, or I mean, when we observe this, we realized that the real issue was the wiring and grounding practice. So it is just like the grounding nuts. It's not the utility. We're not blaming the utility. We are blaming the construction company who did the wiring and especially like the grounding, which creates a grounding issues and grounding loops. This can create, I mean, can make a very bad impact, especially in the computers. The computers are made on from electronics, so they are very sensitive to the power quality problems and especially like the grounding issues. Now, the next thing, sensitive equipment. So, sensitive loads and weak disturbance. So, two key messages here. The first thing, sensitive equipments, microprocessor based equipments are they are not forgiving. So basically, they need a stable voltage, a clean waveform. So any small dip that the motor would ignore can crash a PLC or a server. So that can create a big problem, which make it a very sensitive, especially as again, as I said, the microprocessor based equipments are very sensitive. So when there is a computer, like the brain, the microprocessor, as we know, those are the brain, and it will like, for example, like the PLC or the server, or we can say like the controller, like the Arduino, etc. All of them, we are using them to do the control for a motor or whatever we have. So if we have a small dip of the voltage, if it is not a clean waveform, it will make a bad impact, which will make a misbehave of these sensitive equipments. The second thing, which is the distribution system, those are more prone. Basically, radial feeders, those can longer distances from strong sources with higher source impedance, more switching, more faults. Engineers say that the network is electrically weaker at the fault of the feeders, meaning the disturbance causes large voltage deviation. So I would say that last end customer, or when we have multiple feeders, like for example, like here is like the distribution, or here is the transformer, then there are multiple feeders. Then when we look at the end customer, the customer at the end of the feeder, this is the worst hours impacts of the disturbance, or worst impact of the power quality. So the end customer, the last customer of the network, which is basically the more frequent problems they will see. So we will say like all of this, they will be impacted. Again, like the end user, because we'll see like struggle of the we can call it, those are weak grid, or the grid that can be impacted easy with any small disturbance or any small power quality problems. So in Jordan, many low voltage and medium voltage feeders are radial. Like as I draw here, this is a radial, not a ring. So on the radial at the end customer here, they will see some problems. So long, especially when we have a long feeders, long ruler feeders in Jordan, we have a lot. At the edge, they have a noticeable voltage drop and deeper sags during the faults. Especially when there's a fault, there will be a very big, significant voltage drop. Maybe the fault is not at your end, not at your side, at the other side, or at the other customers, not at these customers, but they will be impacted of that. Big motor starts when there is like, you know, that the motors and the pumps, the compressors, they have the high startup currents, and the capacitor switching as well. They can produce some impacts. Capacitor switching means when we have a shunt capacitors turning on the capacitor or turning off the capacitor, all of them, they have a power quality problems. Again, like the pumps, the compressors, the motor, anything with motors, they have a high startup currents. This will impact, make some voltage drop, and especially when if you are at the edges or at the end customer, this will this the voltage drop will be more significant, which will make a very big events or very big impact on these customers. So power quality problems are not rare events. They are, I mean, happening. any time of the day, or they can be part of the everyday operation. But we need to make sure to reduce them or to reduce their impacts as much as possible. So we need to make sure the system must be designed carefully to make this impact of these events seldom, to make it very low as much as possible. So the thing here, why problems of the power quality increasing? So the thing here, which is in modern power system reality, we have new equipments, especially with the electronics technology, electronics revolutions. This creates a new science, which is I think, I mean, that was in the 90s, which is called the power electronics. When we like we have it right now between us, which is creates the or allow the renewable energy interaction with the grid, which make the renewable energy. In order to be connected to the grid, we need to connect the uh, power electronics devices there. And the other thing, when we have the smart TVs, when we have the EV chargers, cell phone chargers, the routers, the computers, servers, all of them, they had a bad impact into the power quality when there's a rectifier. So now the new equipments are more features, they are very beneficial for us actually, but they are more sensitive. So which is, creates a challenge, which is, creates a burden in the electrical system technology. Yes, we have renewable energy system, those are great. Yes, we have the electronics, those are great. Yes, we have EV electric vehicles, those are great for the environment, those are great for the leisure, those are great for us. But I would say they have a bad impact on the power system, which creates a harmonics, creates a power quality problems. So the thing, we need to focus on the efficiency. And again, when there is a huge usage of power electronics, this will make impacts. And they are 24/7, actually, they are working, which make it less tolerance and for interruptions. This can make, I mean, the other thing, it can impact the, or like when they have like the automation, we have the PLC, variable frequency drive, VFDs, SCADA, anything, we have a logic. Those, all of them, they can be impacted by a bad waveform. So the other thing, which is the capacitor, the shunt capacitors in the distribution line, those shunt capacitors are being used to reduce the losses or to improve the voltages to supply reactive power. But the thing, the switching transient, when you turn on and turn off these switching capacitors, this will make a big, huge transient. That big, huge transient can make a poor power quality. It can make like a significant voltage drop or a significant voltage rise that can impact the performance of the power system. And the other thing impacts the end customers. So they can impact the, for example, as I said, like the routers, the computers, the smart TVs, the chargers, etc. And especially we can notice this in the computers. The computers can reboot, restart the computer by itself for no reason. And like especially like assume you are in the middle of the work, then for no reason um, the capacitor or the computer start rebooting. This makes you upset because maybe you are working on something in the middle of something, then you need to redo it from like spending 2 hours, then after of writing something, then after that it is just like disappears for nothing. That's something, of course, upsets and nobody liked it. So power quality become a bigger topic, not because of utility getting worse, but because load's nature has been changed, and the load's nature getting worse. I mean, is getting worse with respect to the electricity, not getting worse with respect to the customers, because respect as us for customers, we like the new technologies, we like the renewable energy, we like the power electronics, the EVs, etc. But it is like, I mean, the roads, I mean, like when it's getting worse, like when there is, I mean, if the, I mean, the roads, when they didn't, we didn't establish a very good words, the cars getting faster and more crowded, but there will be, for example, like if it is not designed very well, then it will be uncomfortable when we have multiple of, I mean, a lot of cars crowded, getting crowded with cars, but the road is not designed to handle that number of cars. Therefore, we need to fix that road to make sure the road can handle all of the cars, no matter if they are, no matter how can, I mean, how many cars, if it's crowded or not. So we need to make sure to maintain a power system to be working on safe operation without interruptions, or without, I would say, be making the customers impacted. Okay, the other thing, which is some examples that we can mention in Jordan, like large irrigation pumps switching on and off in agriculture areas. We notice this a lot. You can go to the suburbs area, you will see a large irrigation systems. Those are pumps which are based on motors. They can switch on and off. These very big motors that can consume. They have a high startup currents. That high startup current or high inrush current will consume a lot, or will make, take a lot of starting up, making the transients of the currents very high, which will make a significant voltage drop, and this can impact the customers. Also, we used to use the LED lighting. In home actually, like we see that we are no longer trying to use the fluorescent and like the Edison light bulbs. We are right now using LED. Those are brighter, cheaper, cheaper, and they can. The costs, or like they are very energy sufficient. They can reduce the amount of energy usage, and the those are can create some power quality problems, because LED lighting technology based on electronic circuits, this will make any electronics, power electronics, this can impact in the harmonics. And the other thing, which is air conditions with inverter drives. I think everybody is familiar that we have air conditions in the past that consuming a lot of power, and the modern air conditions, and they say like those air conditions come with inverter drives. And we say like when it comes with inverter, this makes fuel usage or energy usage, so you'll see like there's A++ on it, so basically make it very energy sufficient, which will make with any air condition with inverter will make the energy consumption low, and it is making the life easier by reducing the energy usage. Yes, that's great, but the disadvantage of that, because the inverter drives is based on electronics, and the electronics can cause some harmonics. And the other thing, the photovoltaics inverters, as we know, the photovoltaics, those are DC, and the grid is based on AC. Then we need to have an inverter that converting DC to AC, and making the interaction of the photovoltaics into the grid, like it can make harmonics, flicker, voltage rises sometimes, which create a problem. Okay, importance of power quality. Then we need to make sure like the customer awareness and interdependence of the uh, real and reactive power monitoring. There must be, if the power dips, clock resets, people notice. Today, people also notice that because of the internet drops, their smart devices restarts, and their phone chargers makes noise when there's a power quality issues. Then we can say like the PQ clock monitors, they were in the past, but we still can notice that by looking at reset of the computers. The other thing, internet drops, smartphone restarts, etc. The interconnected systems are the key. So one small event can propagate into a bigger operation problem because everything is networked. A small sag can reboot a router, which disrupt cameras, which affects security, which triggers alarms. So sometimes because of this can make a false alarm, or sometimes it can make like disable the alarms. So the power quality is not just a technical quality issue, it can be a service quality issue. It can, like for example, when there's, as I said, like security issue, like with the cameras, if they get damaged or if they are it's not working properly, this will make a problem, a big problem that we don't want. Okay, let's go through a few things like can hidden causes. The first one, server reboots randomly. This is a classic voltage sag or momentary interruption. Servers are sensitive unless they have a UPS, which is uninterruptible power supply. Even with a UPS, again, UPS means uninterruptible power supply. If the transfer isn't fast enough, the UPS is undersized and they still get rebooted. So server can reboot it randomly. The other scenario, which is capacitor fuses blowing repeatedly. So this can happen because of the transient during the switches. So because basically the transients of the capacitor or the switching will make a resonance, the resonance with harmonics or incorrect capacitor bank design, they will work under the resonance frequency that can magnify the harmonics current to a very large value. As a result, the fuse will blow out. So basically, the fuse will be blowing, can cause a problem. The other thing, variable frequency drive, VFD, trip occasionally, but the rest of the planets runs. Oh, variable frequency device, VFD, are very sensitive to DC link under voltage caused by sags or to control power disturbance. Many drives trips to protect themselves while other loads ride through without a big problem. So if VFD getting tripped, this can impact the overall system performance. The other another example, cache register stops working properly. At the point of scale systems, those are basically computers. They hate dips, voltage dips, and noises. If the computers, again, those are very sensitive to the grounding, very sensitive to voltage dip, voltage drop, and very sensitive to noise that can create a trip or can make a reboot of the computer. So especially assume that you are at the cache register and suddenly after you are when during the middle of the work, then start rebooting. This will be very annoying. The other thing, which is the 911 dispatch. So 911 recorder stops, needs resets. So this shows the power quality can become a life critical if the critical systems are not designed with the proper right side through. Like, so that's why, for example, 911, which is again like the emergency lines, if they have a critical, if they don't have, I mean, if they have a poor design, if they don't have a UPS, which is uninterruptible power supply, if they don't have, if they have a redundant supply, then a small power quality events become operational hazards, can get a problems or can create a problems. And the other thing, which is the radio station transmitter, it can trip periodically, which is restarting itself because of the power quality issue. So the thing, engineers must translate complaints into a proper power quality phenomenon. That's the skill. Complaints, waveform events, source. We need to mitigate it and try to make it to solve it as much as possible. So type of the problems. So there are several types of the power quality. Uh, let's think it as a map. So the reliability events, outage, there are total loss of supply, easy to understand, but costly. I mean, power outage, okay. This can be, we can easy to understand that there is a power quality issue because of the power outage. The other thing, long-term and short-term voltage variations. Short-term can include sags, swells, often from, it can happen from faults, motor startup, again, as we say, like high startup current of the motors, or capacitor switching turned on and turned off, while the long term can include under voltage or over voltage due to loading, regulator settings, or feeder designs, especially at the end customer of long feeders. This can have this a permanence or I would say long-term variations. Then in this situation, we need to fix it by changing the tap changer settings or doing a voltage regulation, etc. The other part, which is over voltage transient, lightning strikes can make some transient. Switching, like capacitor switching, can make a big transient. And the transmission line switching, if the transmission line was out of service and we've been re-energized it, then it will make a big events. Transient can be a huge amplitude and very short period because, as we know, the transit is something temporary. But even though it's happening for a short period of time, it's temporary. But if it has a high magnitude, it can make a bad impact into the power system. The number four, steady state disturbances. Those are harmonics, and flickers live here. And like as an example for that, like the power electronics devices that we have, like the LED light bulbs, the electric vehicles chargers, the photovoltaics, etc. All of these things, the chargers, is not only the EVs, cell phone chargers, anything that charge the batteries. So the idea IEEE 1159 exists largely so we can define and monitor these phenomena constantly according to the IEEE standards. So by trying to tie this in Jordan, lightning is a real concern in winter storms. Switching events occur with capacitor banks and network reconfiguration, especially like if there is power outage and reconnect the power, or if there is like recloser, turning off sectionalizers, and harmonics are rising due to the LED drivers, chargers, variable frequency drives. Flickers can appear in areas where large fluctuation loads, welder, crusher, big motors, cycles. So types, the other thing, which is the types of problems, we don't use vague words. So, which is basically warning words like surge, glitch, blink sounds helpful, but they are not engineering terms. If a customer says surge, it means a transient, a swell, a sag, a momentary interruption, or even harmonic problems. Power quality issues or power quality monitor requires precision language because of the solution depends on the event type. As an example, if the event is a sag, a surge protector will do almost nothing. If the event is a transient, then surge protector matters in the lightning strike. If the issue is a harmonics, then the surge protector does nothing and you need to filter or load redesign. So I would say uh, surge arrestor is only being designed for like a transient, like I would say the lightning strikes, while it will not help when there's a sag or voltage drop. It will not help in harmonics because harmonics, if there's a harmonics, we need to use a filter or load redesign to do that, to solve this. So IEEE SCC 22 standards basically, and coordination with IEC and SIGRI is mentioned here. This is basically because the global push to keep terminology aligned. So the engineers don't speak different power quality language. So we need to make sure to make it listed in the power quality issues, listed into a specific thing so we can understand each other by the SAG is not the same thing as the transient, it's not the same thing as harmonics, it's not the same thing as a blink, as a glitch, etc. So we need to make a precise definition. And those can be, the definitions can be in different books. So, it's today's lecture is just an overview, so we will not go in deep details about it. But for your information, you need just to understand there is some definitions that we need to agree on to make sure a constant power operation. The other thing, general class of power system problems. So even if the like every power quality problem can be classified, or we need to ask by two questions: is this a steady state or non-steady state? Or I would say, is this permanent or temporary? That's the thing. If it is steady state or permanent, continuous distortion, continuous imbalance, continuous frequency deviation. If it is non-steady state, which is something transient, something temporary, events like sag, swell, transient interruption. The other thing, which is we need to make sure like where does it originate? Is it from the utility side, from the customer side, or from the interaction between the customer and the utility? These classifications is the beginning of the troubleshooting. If we skip it, then you will waste your time on applying like solving a problem that's does not exist, or solving something else. You are working on something else. Then we need to make sure to think about it. All right. So here, like these characteristic of the power system phenomenon, talking about the category and like the typical duration according to these standards, IEC standards. Okay, so the sources of the problems are basically lighting, nonlinear loads, power electronics, capacitor switchings, temporary and permanent faults. These are the sources. Then we need to make sure the power quality events are electromagnetic phenomenon. That means we need to describe them using the magnitude, duration, frequency content, repetition rates, and energy. So this is exactly why monitoring standards like IEEE 1159 focuses on consistent description of the conducted electromagnetic phenomenon. So in practice, we need to make sure when we install a power quality monitor, we don't just record the data. Then if there is a problem, you will record a signature, but we need to make sure um, record how deep was the sag, how long did it last, which phase, was it a transient or oscillatory? Um, does it repeat every day? For example, is it happening related to the load every day at 2 p.m. or 1 p.m.? Or is it happening only during the storms, which is weather related? Or is it happening because of the customer behavior? So this will help you in diagnose the problem. Then again, it's very important to make sure to understand that the problem can happen as a steady state. As an example of steady state, if there's a problem in the amplitude, if the RMS voltage level is not appropriate, the frequency, for example, if the frequency is not 50 hertz, if it is not, which is not our region, here is, I mean, an example. And the spectrum, if there's a harmonics content, can be a steady state problem. A modulation, if there is a low frequency variations, low frequency harmonics inside it. Source impedance, which is weak network, how weak network do we have? Notch or depth area, which is common with the converter commutation notches, which is basically related to the electronics, power electronics commutations. Or it can be non-steady state, which is, again, it can happen something temporary, which is like the rate of rise, how fast the transient goes, the duration, is it within milliseconds or within seconds, etc. The frequency content, is it oscillatory or just impulse happening once and disappears, or it just like oscillatory and being degraded with time. And the rate of occurrence, is it rare, is it frequently, is it happening multiple times a day? And the energy potential, how much the energy is, to make sure to monitor the damage capability, is it gonna make a big damage or not? So the lighting impulse can be extremely high amplitude but very short. So the key is rate of rise and peak damage is insulation stress. So the voltage sag may not damage insulation, but it can crash control systems. So the duration and depth really matters. This is why customers can report different problems from the same feeder. One customer has a motor mostly tolerant, which is, I mean, that's fine. Another one has PLC, VF, variable frequency drive servers. Those are very sensitive. So same networks, but different equipments. Everyone has different things. One customer complains, the other one is not. All right. Again, like the source of the problems, lightning. Again, let me repeat them again. Lightning can create transients, flashover, momentary interruptions. Protection using like shielding or arresters, surge arresters, proper grounding, insulation coordination. Then we can overcome this problem by this. The other thing, nonlinear loads. Nonlinear loads, those are draw currents in non-sinusoidal shape. Those are creating harmonics. As an example, LED drives, chargers, variable frequency drivers, rectifiers. We can try to solve them by installing some harmonics filters. As an example, shunt active power filters are being used to solve such nonlinear loads phenomenon. The other thing, power quality, is not only power quality create harmonics, they can also be sensitive to sag transients. Power electronics are both cause and a victim, and I would say those are the solver. So power quality are the cause of power electronics are the cause of power quality problems. At the same time, power electronics are the victim of the power quality problems. And the same time as well, power electronics can be used to solve power quality problems. Those are the cause, the victim, and the saver. But we need to make sure to make a proper usage for them. That's the thing. The other thing, capacitor switching. Capacitor banks, again, are used to make a power factor correction and voltage supports, supply reactive power. But this switching can create transient and resonance. The other thing, temporary and permanent faults. Faults can produce sags, interruptions, and sometimes um, impact the unfaulted phases. Clearing the faults and recloser can create repeated sags. So sometimes, because as we mentioned in the previous slides, previous couple of lectures, we mentioned about the recloser. The recloser can be turned on and turned off multiple times. So this turn on and turned off multiple times. This make I mean more voltage sags that can repeated events of sags. Now, the just the mindset that you need to keep it. I mean, the thing that you need to keep it in your mind. Power quality is not solved by one magic device. You can solve it by identifying the dominant phenomenon or the source and match the mitigation to the cause. For example, like if the source of the power quality is the lightning, then make a surge protection, make a UPS, all right, through capability. If it is a harmonics, make a filtering. If it is a grounding, make the grounding improvements. If it is a weak network, make the network strengthening or increase it. If it's operational change, try to redesign the loads, redesign the system, and make voltage regulation to solve this problem. So understanding the source is the half of the solution. Once you understand what's the source, what's the main reason, then the other thing just apply the solution. Now, let's talk specifically about like an example about Jordan, not about the other part of the world. So many books and examples came came from the North America, Europe, where feeders are shorter, networks are meshed, grounding resistance is low, climate is mild. While in Jordan, the reality is different. So what's really affecting the power quality in Jordan, especially in low voltage and medium voltage, because the vast majority of the power quality problems in Jordan, they are not in the high voltage, they are in the low voltage and medium voltage networks. So the thing here, the reasons or the things about the in Jordan, we have radial feeders and long distances, which is most more medium voltage and low voltage feeders are radial, not ring. And this means power flows in one direction and there is no alternative path. So if the current is discontinued from the feeder, then the rest of the feeders will be out of service. So as we move away from the substation, the source impedance increases, voltage regulation becomes weaker, sags becomes deeper, recovery becomes slower, which make it a weaker grid. So the customers at the end of the feeder experience more power quality issues than the customers near to the substation. That's why the same SAG events may reboot equipments in one area while another areas are barely noticed this. So keep in mind, again, in Jordan, here is the substation, and then we have multiple feeders. Then in this feeder, we have sub feeders. Then you can say the customer at the end of the feeder and the customer at the beginning of the feeder. Um, Here is customer A, customer B. Customer B will face many power quality problems while customer A can barely notice a small power quality problems. Again, the reason, because the impedance here will be higher, and the other thing, which is the voltage regulation will be weaker, recovery gets slower. The other thing in Jordan, like the motor dominated loads, in Jordan, it is, I mean, the understanding the load are very important. So, for example, like we have a large water pumps, especially in irrigation pumps, like also in the municipality water, like the water company pumping station, the booster pumps for buildings, the agricultural walls, the industrial as well, industrial areas. These motors, they have a high startup currents, starting high frequency, starting frequently. Those are not soft starter, which make it when their large motor started, the current can be 5 or 7 times the rated currents. which make a significant voltage drop locally. Nearby customers close to these motors, like the irrigation systems, they will face or they will observe a voltage sag and flicker. So that's why, I mean, sometimes students can, or you can think about it, why do lights flicker at night in some villages? The answer is a large pump starting somewhere in the same feeder. That's one reason. Or the other reason, we can say, like, there is a capacitor bank being turned on and turned off. Or some other reasons, like there are a lot of reasons, like power outage in one of the transmission lines, but not us. Then you cannot flickers. Here is an example. The other thing, or also in Jordan, capacitor banks in medium voltage feeders. So to improve the voltage, make power factor correction, reduce the losses, supplying reactive power. Jordanian, I mean, in utilities, we have capacitor banks on medium voltage levels. Those are very good, but they have a side effect. The side effects, transient over voltage occurs, so oscillatory transient appears, sensitive equipments may trip. So if the capacitor switching is not synchronized or properly damped, this will impact the PLC will be tripped. The VFD, variable frequency drives, trips. Electronics matters malfunction. The computers can be resetted. So the routers can be resetted as well. So again, the power quality problems are not bad engineering, but they are often side effects of a good engineering done without full consideration. So, I mean, the people who did the design of the sources of the power electronics, they don't have a bad intention to impact the grid. They have a good engineering by making some good devices that can be very great, but there is a side impact on that, or some you need to take into consideration that the power quality issue. The other thing, which is in low voltage, which is the widespread of the low cost electronics, like the LED light bulbs. Those are cheap. Those are very efficient, energy sufficient. Phone chargers, TVs, receivers, low quality UPS, uninterruptible power supply units. So those are can draw distorted currents. This can inject harmonics into the network, the renewable energy system as well. Those all can have the low ride capability. So this can create power quality issue, increase it, and those are very sensitive to them as well. I would say, like, again, as I said, like power electronics are a reason of the power quality, and which is the cause of the power quality. Those can be as well the victim of the power quality, and again, those can be as the solver of the power quality problems. Then the other thing, which is the climbing, which again, like in Jordan, especially in the summer, we have dusts. I mean, a lot of dust. Heats are very high, and in the winter we have a lightning strikes. So the environment matters. So the dust can increase the surface leakage, making a flashover, especially in the high voltage. Heat can increase conductor resistance, will make the voltage drop. Also decrease the capability of the transmission line, the ampere capacity of the transmission line because of the heat. Lightning cause the transient and momentarily interruptions. So even though the lightning does not strike directly, but nearby strikes can make a transit on the travel through the low voltage networks. Okay, then the thing which is we need to make sure when we diagnose any problem, where is the customer located in on the feeder? The thing which is, are large motors nearby? Are any capacitor bank switchings? What type of loads dominates? How strong is the network at that point? Those are power quality to solve the local problem of the power quality. And the other thing, which is two customers, again, on the same feeder can experience completely different problems depending on the location. Are they close to the substation or not? And depending on the load behavior as well. So we need to make sure just to think about it. Then basically, that's it. So this is the end of today's lecture. Let me stop recording.